Good morning, ladies and gentlemen. If you will please have a seat. And we are going to start a very interesting lecture by Professor Jeff Dror. He's an assistant professor in the Department of Physics at UF and the director of the UF Institute for Fundamental Theory, also a member of the High Energy Research Group of that institute. His research interests are in the study of the early universe and the detection of cosmic fossils, such as gravitational waves created during the collision of black holes and other catastrophic events. Gravitational waves and the concept of space-time through which the waves propagate were originally theorized in Albert Einstein's 1915 theory of relativity. How sad that Dr. Einstein is not around to see the realization of his theory. Professor Dror and other members of the UF Institute for Fundamental Theory collaborate with the international research groups studying gravitational waves. Other UF researchers play a leading role in the Laser Interferometer Gravitational Wave Observatory, also known as LIGO, which first detected gravitational waves in 2015. Professor Dror's work focuses instead on nanograv, a collaboration that uses a method complementary to LIGO in order to detect a different kind of gravitational wave. Professor Dror took his PhD in physics from Cornell University. When space-time sings, echoes across the universe. Please welcome Professor Jeff Dror.
Thank you very much. It's really an honor to be here, and I would love to get to know as many of you as I can during my time. I'll be hanging out after the talk also for questions, and also we'll have lunch here. So feel free to come chat afterwards, and we can learn a little bit more.
I forgot to remind you to turn off your cell phones, or at least to mute them. Thank you.
Thank you. So here is my talk, hopefully a little provocative. Gravitational waves are a fascinating phenomena that's really only been confirmed in the past 15 years. So we think about, this field is old, like Phyllis was talking about it. It all corresponds to very long ago. But this has only really been confirmed in the last 15 years. And in fact, only in the last 2 years, something remarkable happened. We've detected a new kind of gravitational wave. And I want to describe to you what that program is and how that all operates, and also kind of where we can go in the future and how it's complementary to the current discoveries that have been happening in the past decade. Now, I want to start with a poem. And it's about two black holes. Black holes are very compact objects that are roughly the mass of the sun, but can be only, let's say, a few miles in size. So gigantic objects in mass, but tiny in size. And they can meet one another, as you see in this diagram. And what they do when they meet one another is perform a so-called celestial dance. They go around each other in a near perfect circle. They deform space-time in a way that I'll describe for you in a moment, in a cyclic pattern, and they inch closer together over billions of years. And when they come together, there's an epic collision that takes place. That epic collision generates what's called a gravitational wave signal. That gravitational wave signal corresponds to ripples across space-time that journey towards us. They arrive at Earth right here after roughly 1 billion years to be detected by us, a curious civilization looking to study the universe and hear this kind of epic song that's taking place. I love this poem because it gives you a little bit of a feeling for the grandeur of what's happening. We're talking about the most compact objects, these heavy, gigantic mass objects meeting one another, colliding, and we're able to see it right here on Earth by carefully making measurements of different objects here kind of close to us. This is kind of what I want to describe for you. The first segment of my talk will be all on gravitational waves. What is this concept? What are we even looking for here? How do these searches work? And what really produces a substantial amount of gravitational waves? And I'll go over 2 methods that I want to describe. The first one is the one that only 2 years ago achieved a remarkable discovery of a new kind of gravitational wave, and that's using the timing of a very special star called a pulsar. In fact, many pulsars, as I'll describe for you. And then I want to describe for you another method, a method that I'm currently developing that's based on a different kind of source of light that we're tracking called a quasar. And then I'll summarize to finish out this session. Now, to get a feeling for what gravitational waves really are, I want to use an analogy. And that analogy is sound waves. That's shown for you on the left-hand side of your screen. On the left-hand side, you see my newborn child. He's only 5 weeks old, sleeping peacefully in the bottom left-hand side. And this is us, sitting in the retirement community right here. Now, he's not always as cute as he is right now. Sometimes he decides to scream. When he screams, something remarkable is happening. The air molecules that are surrounding the room start to vibrate. They collide with each other. Those collisions begin to send over a signal from us to hear his cry, and that travels across far distances, in some cases, all the way to the listener. Now, I want to highlight 3 key aspects of this process. First one is the medium. What is providing the motion of the sound from location to location? That's these molecules in the air, the ones that we can't see with our eyes, but they're everywhere. What sets the sound? How high is the voice of, in this case, Ezra, my baby that you see over here, is the vibrations inside his vocal cords. They're shaking back and forth in a certain frequency. And how fast they shake tells us how high a pitch we hear from his voice. And the amplitude, it's a little covered by the bottom there, is set by his his screams. Now, gravitational waves in many ways work analogously. I'm not sure why it's not working for me. Work analogously, and that's what you see on the right-hand side. There's 2 things that I want to have you keep in mind to understand why we have gravitational waves. One is that everything that has a mass deforms space and time. We are living in some universe where we're right now present in space and time. We have a certain location where I am and what time it is. And anything that has mass deforms that. It's a very abstract concept, perhaps. A nice way to think about it is in terms of this 2-dimensional surface that you see on the right-hand side. Every single point there represents a point in space-time, physical space in this case, and this little indentation is the fact that some mass is here, maybe a black hole, maybe something else. It deforms space-time. But there's a second property that I want you to keep in mind, and that's that there's a universal speed limit. Nothing can propagate faster than the speed of light, a concept you might have heard about before. And that means that if you have such a mass like this that begins to move, different regions are going to experience this gravitational message that it's sending over in a delayed way. And this sort of effect causes ripples in space-time itself. So not only do we have this fundamentally large deformation at the location of the mass, we also have these waves that form. These waves are precisely what I mean when I say gravitational waves, or the fact that space-time itself has now these ripples that are happening, analogous to the ripples that we have in the case of sound waves. Now, there are 3 things that I want you to think about here. One is, what is the medium? What is sending the message? The message is being sent not by some particles colliding with each other, but space itself is shaking back and forth. A fascinating concept. The frequency of these waves that are being set are set by how fast this object is moving. If it's going around in a circle, it's set by the period of the object's motion. And how large the amplitude of the gravitational waves is set by the mass of the particle, or the mass of the object, I should say, which is going around in a circle. Now, this story could have been told for anything. When I shake my hand like this, gravitational waves are being formed. However, it's not forming very much. When do you get a lot of gravitational waves? It's when you have very heavy objects that are very small hitting one another. And Maybe it's not too easy to see on this diagram here, but what you're seeing there are two black holes in a simulation hitting one another. And these black holes, again, are very heavy in a very small space. When they collide, they undergo an epic collision, and that collision produces a lot of gravitational waves, a lot meaning enough that we can see them. They're not going to kind of jiggle me in a very substantial way if I'm not paying very, very close attention to what's happening. And trying to discover these sort of gravitational waves is precisely what I want to describe for you. How this effort takes place is really the heart of this talk. Here is a depiction of the Earth in space-time. So these sort of lines, again, are your space, and the Earth, that's where we're sitting and listening to this lecture. If you wait some period, if a gravitational wave is passing through, you see space is being deformed back and forth. As you wait, you see these sort of vibrations that are happening. But in order to see these sort of things, you have to find some way to know, is my space around me moving? What sort of ruler, what sort of measurement can I make to know whether these sort of effects are happening? And remember, these are very tiny effects. So I can't just, build a ruler and stare at it with my eyes to know whether we have gravitational waves passing by. I need to be very clever about how I conduct this sort of experiment. And to understand how to do that, the first thing to know is what's called the equivalence principle. This is a notion that was developed all the way back by Einstein in the early 20th century. And what this tells you effectively is that in order to know that my space is curved, in order to know a gravitational wave is really passing by in this room, I have to build a big experiment. What does big mean? It means big enough to see the curvature. If I'm building a very small experiment, I'm not going to be able to see a very significant curvature. I have to build a very large experiment. And that suggests the idea of perhaps we want to use some sort of distant light sources. Distant light sources can provide us an opportunity to build a sort of space-time ruler, if you wish. And by tracking these distant light sources extremely precisely, we can in fact learn that gravitational waves are passing by us. And this comes to the two types of methods that I want to describe for you. The first one is the timing of these kind of special pulsars that I'll describe for you what they are. And the second one is quasars. That's these two ideas depicted on the top left and right-hand side. Is there a way to take down the black bottom there? Oh, great. So here on the bottom of your screen, what you're seeing are different black holes masses. Now, black holes, as I mentioned for you, are the dominant source of gravitational waves that we often see in our universe. And they have masses that are as low as roughly as heavy as our sun. The sun is pretty heavy, but it's in fact the lowest kind of mass black holes we know about are roughly that mass. But what's really fascinating is that they also go up to maybe about 1 billion times the mass of the sun. So these can be extremely heavy objects, really fascinating in size. The nearest black hole that we have to us is roughly about 10 solar masses, so 10 times the mass of the sun. LIGO is an experiment that I already, or Phyllis actually briefly mentioned for you. I'll describe it a little bit more in a second. It was the first experiment to detect gravitational waves directly. And the black holes that generated the gravitational waves that LIGO saw had a mass roughly at this point, about 30 solar masses or so. I want to talk about much, much heavier objects. The objects that I want to talk about are the sort of 1 million times the mass of the sun, 1 billion times the mass of the sun. These are extremely heavy objects, and you might wonder why we expect them to be there. And the truth is that we don't really understand their origin, but we know that they're there. The Milky Way, our galaxy, has a very heavy black hole in the center of about 10 million solar masses. Other galaxies have even larger black holes. These black holes, because we're not very creative, are called supermassive black holes. They're very massive. Now, when you have a very small mass black hole, it's relatively small in size, and so it produces a gravitational wave signal that's relatively high in frequency. It goes in the inverse to its size. So the LIGO gravitational waves that were detected were in the sort of relatively higher frequencies, maybe corresponding to 10 hertz, 100 hertz. That's roughly the same kind of frequencies that our ear hears. We hear in roughly in the hundreds of hertz kind of ranges. Just a coincidence. But if you're looking at much heavier black holes, these supermassive black holes, the frequencies are very, very different. They correspond to much, much lower frequencies. And to give you a feeling for how low, the kinds of gravitational waves that I'll describe for you in this talk and their detection will be about 1 billion times less than a hertz. So that means that over 10 years, these things maybe oscillate one time. So if I have, let's say, my hand here, over 10 years, I'm looking at my hand go up and down like that. So I need to build an experiment that's sensitive to an extremely long time scale. And that's the challenge of trying to see these sort of heavier objects. And that's what these sort of pulsar timing and quasar timing ideas are targeting. In fact, there is something very unique about going to such low frequencies to look for gravitational waves. There's a different kind of source entirely, not related to black holes, having to do with our universe. And I'll discuss for you a little bit about how that operates towards the end of this lecture, if I have time. Now, the different techniques to look for these sort of gravitational waves, I've already mentioned briefly a few of them, but I'll summarize them for you on the top. The first one is the one that the University of Florida operation in the physics department has been a huge part of developing, and that's the sort of LIGO experiment that I briefly mentioned. The idea there is to build lasers that travel long distances. Maybe they travel a few miles back and forth, back and forth, back and forth. And if you have a gravitational wave passing by that oscillates maybe once per second, you can try to look for the laser light and study its properties and look for oscillations of that laser light over time. That's the idea of the LIGO experiment that successfully looked for gravitational waves and detected them back in 2015. There's something, a big development that's happened in the past year or so, and that's that we have decided as a community to build a LIGO kind of experiment in space. This experiment is called LISA. It's now funded. It'll be primarily a European effort, but also funded by the other countries, including the US. And it'll essentially be LIGO in space. It'll now be huge travels for lasers, but it'll be kind of a similar kind of technology. We're just building lasers, shining them across solar distances and back. A remarkable achievement, and I'm excited to see it develop over the years to come. What I want to talk about are two other ways. They're targeting these sort of lowest frequency opportunities, these sort of gravitational waves with the lowest possible frequencies. And they can look for things like these supermassive black holes that I was just mentioning to you. That's pulsar timing is depicted for you here. I'll describe for you what that is soon. And here, again, I'll describe for you what this is soon, is sort of quasar timing idea. Okay. And now we can get to kind of the heart of what I want to describe for you, this idea of looking for timing of these pulsars. If we can move that one more time, great. Now, in order to understand this sort of technique, I want to first go over where a pulsar comes from. It comes from an object like the sun. Our sun, for example, it can go through a process called a supernovae. A supernova is a remarkable event. It happens about once every century in our galaxy, or a galaxy like ours. And it's when a star explodes. The star explodes and sends out a huge amount of energy in all directions. And in fact, when that happens, we see so much light from that one star that it supersedes all the other stars in our galaxy. It's an amazing historical exercise. You can see people throughout history remarking, this star over here is getting suddenly brighter. We don't understand why. And it happened roughly every 100 years in our history books. You can see this. And we're waiting for our next supernova to happen in our galaxy. We're kind of really excited to see that in the near future, hopefully. But when that happens, something special gets left behind. And that's either a neutron star, a very, very dense star, or a black hole. If it's a neutron star, it's possible this star, which is basically a bunch of particles very squeezed in together in a very tight formation, If you have this sort of neutron star, it can form beams shining on either side. That's what you're depicted over here. In this special configuration, it's what's called a pulsar. It's effectively just an extremely compact star, perhaps a solar mass in mass, squeezed into a few miles in radius, and it has beams shining on either side. But what's special about it is that it goes around extremely fast. This star can go around on its axis about 1,000 times in a second. So we're talking about extremely fast rotations that are taking place. And if you can go ahead and build a telescope and stare at one of these, what you'll start to see is you'll see intensity of light going up and down 1,000 times in a second because you have a beaming axis. So whenever the beams are facing towards your telescope, you get a little excess of light. And whenever it's not facing your telescope, you get a depression in the amount of light that you're seeing. And so you can label these. You can call this pulse 1. That's the first light when it goes to the peak. You can call this pulse 2, pulse 3, pulse 4. And then you can make a plot. You can say, when did this pulse arrive at my telescope, and when this one arrived at my telescope, etc., etc. And why this is a powerful technique is because now you're able to time something. You're able to look at the time of something over the span of decades in this case. And that's in fact what we do. And we have, it's kind of thinking about looking at a dreidel, if you wish. A dreidel goes around its axis again and again and again. If we time, we can study and learn about space-time around that dreidel as it's going around by studying when it goes around every single time. And a pulsar is like a very, very good dreidel. Now, if you have gravitational waves, it'll change this picture. If I have just regular space, you'll see a pulse come at you once every time the pulsar goes around. It'll kind of tick like a very good clock. But gravitational waves will muck everything up. They'll change space-time between us and this pulsar. And hence, we can learn that by studying the time of arrivals of these light pulses. Now, because this pulsar is so stable, nothing is really influencing it significantly over our lifespans. Because it's such a stable dreidel in this case, we can look for extremely low frequency gravitational waves, the kind that I was already emphasizing to you, with frequencies of maybe 1/1000th of a hertz, so a billion times less than a hertz, the kind of gravitational waves you expect from something like a supermassive black hole. Now, this has been known for a few decades now, and there's been collaborations formed around the globe that are targeting these sort of gravitational waves by studying these pulsars. There's an American effort called the Nanograv Collaboration. It's one that I am also an associate member of. And this has been kind of operating, like I said, for decades, but something very special happened 2 years ago. 2 years ago, we saw something. We've been looking for something for decades. We've been trying to use this technique, studying this sort of light arrival times for decades, but 2 years ago, we were the first ones in the Nanograv collaboration to detect these gravitational waves, just by using the technique that I described for you here. Now, my group in particular is targeting these sort of pulsar timing searches, trying to understand how they can work better and better, and building new types of techniques to look for these sort of gravitational waves. There's different sorts of searches. It's a big collaboration of about 200 members, and we're all actively trying to develop better and better tools to study and understand this gravitational wave signal. Now, how do I know for sure that we saw gravitational waves? And that's by a very special property. We're not looking at one pulsar. We're looking at many of them. There's roughly 68 pulsars that Nanograv in particular is studying. And gravitational waves imprint a very special pattern. They tell you that if I have a pulsar over here and a pulsar over here, I can predict for you what is their relative size of time delay that you expect. These are called correlations in the pulsar timing data. I know a particular correlation I can predict due to the property of gravitational waves. So if I have some angle between the two of them, there's a very special function that I can predict for you, theoretically, for what I expect these correlations to be. And by itself, if you didn't have these correlations, maybe you're not really understanding your clocks, maybe something funny is going on, but these correlations that I'll show for you in a moment are indicative. There's no other way to fake these things. If you can find them, you for sure are seeing indeed gravitational waves. Now, this is, as I said, already a massive effort. It took 68 pulsars for decades, looking at these things roughly once every month, with extremely precise telescopes to study when the arrival time of light came. It's a very large collaboration. And finally, after years of work, we produced a plot as shown for you on the top right-hand side. Now, this plot shows you the correlation strength. How correlated are pulsars in the sky as a function of their separation in degrees on your horizontal axis. The key point that I want you to take away from this plot is simply that this black line over here is what general relativity predicts, and these blue markers here tell you what the experiment actually found. And it's in remarkable agreement. This is where my confidence comes in, that we detect gravitational waves for the first time with this new technique. So what did we actually learn about? And this is where the future of this science is coming. We're now trying to understand the signal. We know we have some signal. We believe the signal is coming from supermassive black holes all over our universe that are acting in concert. So it's a very special kind of signal. It's not a single supermassive black hole that's present, let's say, in this direction, but in fact, it's all of them. They're all acting in concert. They're merging together, and billions of years later, we're here sitting and studying these pulsars and learning about these black holes that are merging with each other. And that's what you're seeing in this picture over here. So maybe we're sitting somewhere over here. Our space-time, which is denoted by these sort of grid lines, is curved, and we're studying that by learning about the pulsar light that's arriving to us. Now, the next steps kind of going forward in this program is to understand the signal. Why does it have a certain size? What is the distribution of kind of gravitational waves that are arriving at us? What are the properties of this gravitational wave signal? And also, what can we learn about what happened in the very early universe? These gravitational waves are from a very long time ago. They're from when the universe was much younger. We can study this gravitational wave spectrum and understand the properties of the universe at that very early time, and that's what we're right now working on as a collaboration, among other things. Okay. And with that, I want to move on to this second technique to look for gravitational waves, and that's quasar timing. Again, the name of the game is going to be look at some distant source, study the timing of arrivals of light from this distant source as much as we possibly can, and see what we can learn about this source. Now, the reason why a new technique is required here is because pulsar timing has a certain amount of time that we're observing for. We're observing pulsars now for decades, and excuse me, 1 over a decade, an inverse of that time scale corresponds to the frequency at which we're most sensitive. So it's an inverse relationship, and that corresponds to a number of about 10 to the minus 9 hertz. This is what I told you earlier. A billionth of a hertz is roughly how kind of the target of these sort of searches using pulsar timing. And the reason why you're really limited to this sort of range, it's twofold. One of them is how long we observe for, but the other one is just because pulsars, at the end of the day, are not that far from us. Most pulsars are about 1,000 times as near as the nearest star to us. They're still in our galaxy. They're pretty close by. And so that limits how much you can look for in the lower frequency gravitational wave part of the spectrum, because I told you that you have to scan large regions of space to learn about gravitational waves at very low frequencies. So that requires a new tool if you want to go to lower frequencies. And the new tool that I want to propose, and I've been studying for a little while now, are quasars. A quasar is a fascinating object in its own right. It's depicted here by an artist on the bottom right-hand side of your screen. It happens to also be a black hole in the center of this object, and what it's doing is it's accreting a lot of matter around it. When it accretes this sort of matter, it's going to collect that energy, and it's going to shoot it up in a very vibrant pattern in all directions in the sky, and that's what's being shown over here. Now, quasars are on the other side of the universe. So they are not nearby by any means. They're not in our galaxy. They're on the other side of the universe, typically. And the only reason we can see them is because they're so darn bright. Because there are these extremely energetic processes that are taking place, they're emitting out such a bright light towards us to see them, and we can see them all the way from our telescopes here on Earth. Here you see a telescope that we've been kind of an artist rendition, if you wish, of one of these telescopes, looking at a quasar somewhat far away. Now, there's a very special property of Einstein's theory of general relativity that I want to highlight for you, and that's that gravity bends everything. Gravity doesn't just act on planets, it doesn't just act on apples falling from trees, it also bends light itself. So if I have a quasar that's very far away, and I get a little lucky, maybe I also have some galaxy in between me and the quasar. That happens just by chance. There's maybe a million quasars that we know about. Once in a while, there'll also be a galactic lens, if you wish, in between us and the quasar. And if that's the case, the light that's ejected from the quasar is not going to come straight to us. Instead, this sort of galaxy in between will act similar to the way your eyeglasses work. It'll act like a lens. It'll focus in light from different directions towards you. So if we're looking at this quasar with our telescopes, we don't see light coming straight here primarily. Instead, we see light coming in a sort of bent pattern. What does that correspond to in practice? It means that you see an image that looks kind of like this. In the center, you're seeing the galaxy that's in between. That's this thing over here. But you're seeing now multiple images on either sides of this a quasar because of this bent light. Now, this is only a schematic. I wanted to show you here a picture of how this looks like in practice. Hopefully, you can see it also in the back. Here, we're looking at some quasar. That's the center yellow area over here. And we're seeing two images. We're seeing the exact same object. I want to clarify, the exact same object multiple times in the sky because of these sort of lenses. This is also what you, again, would see with your eyeglasses. You take them and put them next to and between you and some light source, you might see multiple copies of the same image. The same thing is happening here just by pure general relativity, just by pure gravity is causing this amazing phenomenon. And this is called strong lensing. Here you see other ones, just to kind of give you a feeling for how they all look like. You're kind of the typical situation to be in is, again, you have some sort of thing in the center here that's causing the bending of the light and the emission of the light, and we have copies of the exact same image. You might have 2 copies, as shown here. You might have 4 copies, or perhaps even more, as shown in the other diagram. These are all different quasars that we're looking at that happen to have a lens in between us and a quasar. There's roughly 1 million active quasars in the current observable universe. The universe that we have access to is roughly 1 million of them. But of course, most of them are not lensed. You don't often get so lucky that a galaxy is in between you and the quasar, but there are still a lot of galaxies out there, and sometimes you do. And there's roughly about 400 lensed quasar systems that we already know about and have been studying for a little while. Now, there's a fundamental rule that you have to keep in mind to understand these quasar systems, and that's that, again, taught to us by Einstein about 100 years ago, light travels at a finite speed. There's a universal speed limit, as I already mentioned for you. So you have light coming for you from this distant quasar, but it's not coming instantaneously. You don't get to see it right now. You get to see it, what it did 1 billion years ago, a long, long time prior. And that means that if you stare at some image, some quasar over here, and you're in your telescope over here, and there's this lens that's over here, if you imagine looking at this thing as a function of time, I drew for you a little clock here, perhaps the quasar undergoes a flare, just to give you a little bit of a feeling. Maybe it suddenly increases in how bright it is at one particular point in time. And this happens, by the way, quite routinely. Now, if that happens, then as light is traveling in these 2 different paths, as the time is passing, you're going to have one of these images arrive at your telescope a little bit sooner. So you have 2 trajectories of light, but one image comes a little sooner. Let's see that one more time. Here we just have time coming, kind of passing by, and one of these comes a little bit sooner. So that means that you can now track the luminosity, how bright one of these quasars is as a function of, one of the quasar images is as a function of time. And for one of them, you'll see a peak over here, and for the other one, you'll see a peak at some other time. This would be, for example, this image over here. This second one over here would be the image on the bottom. And there's a little time delay. Now, time delays get me excited. Remember, time delays are what we use to look for this sort of gravitational waves using pulsars. Whenever you have a time delay, you can now study that time delay and learn about what is the space-time doing between us and some source. So again, I want to use the same sort of ideas that I already described for you, but now using these sort of novel sources. Now, gravitational waves would not surprise you, I hope. They also would modify this time delay. They modify everything to first kind of the leading order. They always modify everything that you could imagine. And they'll also modify this time delay. So if I can study this time delay, if I can predict and measure it extremely precisely, I could also infer the presence of gravitational waves in the system. And that's something that my group is currently actively working on. Here's my postdoc, Mia West, at the University of Florida, and we're trying to understand how sensitive these sort of methods can be for gravitational waves. And our current estimates are that you can really do something phenomenal with these sort of measurements, and that's what I want to describe for you just right now. And that brings us to kind of a point that I brought up briefly earlier. So what is there actually to see here? What kind of gravitational waves are relevant in this sort of very, very low frequencies? Remember, I told you that pulsar timing is very good at 1/1000th of a hertz. It turns out that quasar timing is good at frequencies that are 1/10000000th of a hertz. They're extremely low frequencies, as low as you can possibly imagine going. In fact, over the entire universe's evolution, these sort of gravitational waves oscillated once, maybe 10 times. These are extremely low frequencies. Why would you ever imagine something in our universe would produce such a low frequency signal? And that's because the universe itself had a very rich history. We've been studying the universe's evolution for a long time now, about 100 years. We've had a decent understanding of what's going on now. And that's by studying the stars out into the sky, the galaxies in the sky. That's what you're seeing here in the right-hand side. And we've studied their evolution as a function of time. You can look for older galaxies and older galaxies. We were briefly chatting earlier about the James Webb Telescope, a telescope that's been recently shot up into the sky and is now actively studying the oldest galaxies we can know about. And we've also looked at things that happened even earlier. Something very remarkable happened in the mid of the 20th century, is we were looking for light, stray light all around, and we found kind of light that's present from all over the place. So if you build yourself a telescope and you look here, you build a telescope and you look here, you'll see light coming in. Now this light corresponds to radio waves, so it's radio wave light. But what's really fascinating about it is that it's exactly the same frequency. It's the same color effectively, coming in from all directions. So you're looking at light here, and you're seeing the same signal. And that's puzzling from the point of view of a cosmologist, because it tells you that different directions should somehow have known about each other in the early universe. This way had in some kind of, they knew about each other. How could otherwise they be at the same frequency? And we understand that today as likely been because the universe underwent a very special period of rapid expansion. It expanded so fast that different regions of the universe used to actually be touching one another, and now they are not. This period has a name. It's called inflation. It's not the same as the inflation giving everybody a lot of trouble these days, losing our bank accounts. It's a different kind of inflation, one that we had this sort of rapid expansion taking place. And inflation has a prediction. It predicts that the universe was moving away so rapidly at that early time, and there was little fluctuations that were happening during that period, and those fluctuations produced gravitational waves. This is the most reliable way to prove that inflation actually took place. So far, we don't know. It's just the leading theory we have towards why we have this light coming from the early universe that happens to be so similar in all of its properties in all directions. And these processes here would produce gravitational waves precisely at the kinds of frequencies that quasar timing can hope to see. And that's what my group right now is actively trying to pursue. Now, will quasar timing indeed prove inflation? I don't know. It's right now being developed kind of actively here at the University of Florida. But this is something that can hopefully be done in the near future. These sort of quasar telescope experiments have been operating for some time. They have a lot of data. And we could look at these images and study the arrival times of light. So it's not a futuristic thing. We can already do it today. We just need to understand the tools that we're looking at. And with that, I want to kind of move towards the conclusion of my talk. The big emphasis that I want to put for you is that this sort of low-frequency era is here. LIGO is the experiment that in 2015 was the first to see gravitational waves, but it saw a very particular kind of gravitational waves. And we've now moved towards an era where we can see much lower frequency gravitational waves with hopefully whole new types of sources to look at. Things like these supermassive black holes that I was alluding to, and perhaps the universe's expansion itself. Here's a picture denoting for you a little bit about what I talked about for you today. We have different things like pulsars that are shooting light on either side, that are spinning around, that we're tracking. We have quasars that are also being shown in the diagram very far away that are sending light towards us. And that light is being bent. And we're studying the arrival times of light of different images inside our telescopes. And through these sort of techniques, we can learn about these black holes that are merging very, very far away, and perhaps the universe in itself, experiencing these tiny little ripples that are happening all over the place. Now, it is I am also the director of the Institute for Fundamental Theory, like Phyllis mentioned, so I do want to highlight a little bit about what we're doing at the Institute. This is our physics department, which is not too far from here. The IFT is a theoretical science endeavor. We're 22 faculty. We're working on different topics within astrophysics, biophysics, high energy physics, mathematics, and condensed matter. And we're trying to bridge that gap. As you can see here, this kind of science that I spoke about today is actually also bridging that gap. It really works at the interface of astrophysics and high energy physics. And we have many different efforts across these different disciplines that are in this sort of same vein. In general, the IFT hosts international workshops. I hosted one last year. We bring people from all over the country and all over the world to study a particular topic. In fact, in the spring, I will be hosting a workshop on these gravitational wave detection techniques that I just described for you. So this is kind of the efforts that we're interested in pursuing and have been pursuing for some time now. We have a regular visitor program. We bring people from all over the place to come visit here, speak to our department, learn about what they're up to. And we're also studying or funding graduate students with our current efforts. And we thrive on support from the community, both by donations and from the returned overhead from our grants. If you're interested in, by chance, donating to the IFT or to anything in particular in the physics department, please let me know. I would love to facilitate that. Or we can just chat about physics as you please. And I'll leave it there. Thank you.
How do your brains feel? Mine is stressed. Bob.
I have a bunch of questions. I'd like to ask you two. I have a bunch of dumb ones, and hopefully these aren't too dumb. The first one is I've read in various articles that the collision of two black holes was detected by LIGO, for instance, and that one weighed 36 solar masses and the other weighed 14.369 or something, very precise. I can see how you can measure the total mass with the amplitude. I don't really get how you measure the individual masses. So that's question one. The other question quickly is, you talked about using gravitational waves for studying the early universe, and obviously you're working on the quasars to do that inflation. Have gravity waves, studies in gravity waves to date, told us anything new about the early universe that we didn't know through other techniques?
Very good. So for the first question, it's because LIGO is an extremely precise instrument that doesn't just give you one number. So what LIGO sees is it has two mirrors, and it's studying the light pattern of the light from these sort of lasers that have gone back and forth. And it's able to see basically how far the mirrors are as a function of time. So you can draw a picture about what is the distance to the mirror as a function of time, and what you'll see are little oscillations that are happening. And those oscillations are literally the gravitational wave passing through and modifying the trajectory of light. Now, because we see a whole event that's happening, we see the thing happening as a function of time, we can study what's called a waveform. We can study how this thing evolves as a function of time and learn about the entire system. So you don't just get one number, gravitational wave or not gravitational wave. You instead learn tons. You learn about the masses, individual masses. You learn about the spins of these black holes. You learn about their distance as a function of time, maybe some properties, maybe they have other forces that are present there. You really have a whole slew of information you gain because you're studying this thing evolving as a function of time. And it all happens within, let's say, a second roughly. So you get to kind of, LIGO operates continuously. It's constantly trying to look for gravitational wave events that are present. And over a span of a second, the mirrors kind of get jiggled in this funny pattern, and then they have this data on tape. And they can analyze that data very, very precisely and learn a lot more about the sources. Now, it's very different than pulsar timing, in fact. With pulsar timing, you're seeing all of the black holes in the universe simultaneously, which is amazing, but it's also not as informative because you don't get to learn about one particular event, which has a lot of rich information. So it's kind of a complementary kind of idea also in that sense. For your second question, you learned something new about the universe. We actually had no idea really how many black holes merged. It seems like a thing that we should know, but it's very hard to predict because black holes don't come from very, very far away and slowly come together. Something triggers their merger that happens. So it's usually you have two black holes that are kind of going around and around and around and around, and then maybe a third black hole comes in and messes up that system. And then it brings these two things together and they start to merge. And what that means is that it's very hard for us to predict these sort of complicated dynamics that are taking place. So in fact, before LIGO got its discovery, we didn't know when it was going to happen. So people were investing billions of dollars with the hope that it was going to happen within the next decades. But they had no idea that 2015 was going to show anything. And the fact that it did is a remarkable kind of achievement, and it's taught us a great deal because we had no idea how often this was going to happen. And the same thing happens in pulsar timing. So there we have supermassive black holes that reach one another. Supermassive black holes are present inside galaxies. We have no idea how often galaxies merge with each other. We have some guesses, but those guesses can be off by huge numbers. So until you make the measurement, you actually don't really know much in this business. In fact, almost all we know about from these processes is from the measurements of the gravitational waves themselves.
I remember attending a talk here probably in 2017 or something, where the presenter had the sound of the two black holes colliding. I thought that was really cool, for the sound of the gravitational waves. He played it.
It's beautiful, yeah.
Yeah, it's quite fascinating. I'm just curious about an idea. Is the multi-universe, in your mind, a reality, or is it a science fiction?
Very different comments. Let me just say for the first one, for the audience who might have not known this phenomena, so in LIGO, the gravitational wave events are in the same sort of frequencies as what we hear in our ears. So it's very natural to actually play a sound bite. You can say, suppose these gravitational waves were actually vibrations in the air, how would that sound to us? And there's a very beautiful kind of chirp sound that it makes, like a bird almost, of a gravitational wave. And that's what led to those beautiful images or the sound bites that you were mentioning. For the second one regarding the multi-universe, I would say I have yet to find a conclusive kind of non-philosophical experimental observation that could kind of differentiate these questions. So for me, I'm an experimental guy. I'm a theorist, but I'm interested in experiments. So whenever my whole focus has always been, what can we show or not show in experiment? And the multi-universe idea, this idea that maybe we have many universes that are showing up, and it never felt that tangible to me because I don't really know of any experiments that could say anything concrete about it. So I don't really think about it a ton because I'm yet to see an experiment that could possibly even probe that question.
I find the whole thing confusing oftentimes, especially with the complexity of the universe. And so the differences between pulsars, quasars, and black holes, how are those connected? Are they different sizes of each other, or how would you describe them as a unit?
Wonderful. So our universe in general has a huge zoo of interesting objects. Earth is a pretty interesting object for many people. I mean, the sun is very interesting. There's also a huge numbers of different kinds of stars. So stars are not a uniform concept. There's many different kinds of stars. Some are 100 times as heavy as the sun. Some are roughly the sun's mass. Some are blue. Some are red. And there's different kinds of stars. So that kind of gives rise to a rich number of phenomenon. And when a star explodes, it can leave behind different kinds of remnants. The explosion is not perfect. There's something left behind at the end of the day. And the thing that's left behind when a star explodes can be of two major forms. One of them is a black hole that I already mentioned. And what a black hole is nothing so fancy. It just means that there's so much mass densely packed in there that light cannot escape. Gravity is so strong for that object that they're black. We don't get to see anything that comes out of these black holes. There's also the possibility that there is a very dense remnant, but it's not that dense. It's not as dense as a black hole, and it can be a neutron star. In that case, you have matter that's really, really tightly packed, but it can still produce light that escapes from either side. And that produces the sort of pulsar phenomenon that I was mentioning. So it's two kinds of possible remnants that take place after a supernova explosion. I would say, going to the quasars, they're a related phenomenon, but a little different. For a quasar, you actually have a supermassive black hole that's present, which happens to have a lot of matter that's surrounding it. And it's eating up all that matter, constantly eating it up. And it's so much energy that's being packed, eating up by the black hole, that it's now shooting out energy in all directions. And that's what we're seeing in our telescopes. So there's such a rich amount of phenomenon in our universe, and we're constantly learning about these. It's kind of amazing. You might think that we've already seen all the things, but only about 10 years ago, there's a very special new phenomenon that started to show up called fast radio bursts. Maybe some of you have heard this phenomenon. And it's the fact that different parts of the sky have kind of radio waves coming at us from different directions. We don't understand it. So there's sort of like, we're still actively trying to understand all the constituents of our universe. It's much harder than you think because not everything is as vibrant as our sun that's so close to us.
I wanted to ask a question. We think about the Big Bang, and then you talk about inflation, and you talk about light now coming from all directions, which is kind of a mind-blowing phenomena. But the question of these ancient, I guess, massive black holes, there weren't supposedly stars that could have come together to have formed these things. What are you thinking theoretically about how these ancient black holes could have formed?
Very good. That's actually an active area of research. So we don't really know. These supermassive black holes, like the one we have in our center of the Milky Way, we don't really know where it came from. It's possible that they came from early stars very different than the ones that we have around us today, stars that were way heavier. Because in the early universe, it's possible stars could have been much heavier than today's stars, maybe 1,000 times as heavy as the sun. These stars are special. They're called POP3 stars. And these sort of stars might have collapsed to produce heavy black holes. And through a kind of different phenomena, ended up leading to these supermassive black holes in our galaxy that are very old. But we don't really know where they came from is the truth. We're still trying to understand that today. And the James Webb Telescope, for example, that I briefly mentioned, it's finding galaxies and supermassive black holes that are much older than we expected. And that's still kind of pushing our ideas of what possible phenomena could happen in the early universe. So in some sense, the early universe, we know a ton about it. We know, these amazing story I could tell you about what happened, about how atoms formed, how nuclei formed, how galaxies formed. There's a whole beautiful story I could tell you, but we don't yet know a lot of basic questions, even still. We're still trying to understand it today.
Clearly, you are quite impressive at taking an enormous amount of data and analysis and communicating the implications so effectively. I was wondering about the capacity of current day computers to do the analysis necessary, and what about the potential for quantum computers to move us further ahead?
It's a major problem. So just to give you a feeling for how big this problem is, so pulsars, we track roughly 100 of them. They have light coming every millisecond, 1,000 times in a second. And this is happening for decades. So you have to store now 10 to the 10 inputs of data for every single pulsar. And there's 100 pulsars, maybe 10 to the 12 inputs of data. That's way too much data, more than a computer could ever hope to store. So we don't actually do what I just described. We have to find some clever ways to process the data, and we're actively doing that. So you kind of need to group the data in a certain way to make it tractable, to actually do the analyses. And it's still a very challenging process. So the nanograv experiment, it takes about a month or so to run the analysis. A month of computing time. So you're just waiting there for a computer to run for a whole month. And we're getting more and more data all the time. There's more telescopes, more pulsars, we're seeing more. It's going to get worse and worse as time goes along. And it's not totally obvious what to do about that problem. One way to solve the problem is to use AI. AI, or machine learning in particular, is a very powerful tool to compress data sets effectively. In fact, I worked on that as a way to develop pulsar timing in the future. We might have to rely on those tools, and we showed that it's possible. Nothing is perfect. We're still trying to understand how to best balance the needs of making the analysis as kind of clear as possible and interpretable as possible and computationally feasible. It's a major issue, kind of trying to figure out how to do that. Now, regarding your suggestion of quantum computers, definitely possible. That'll play a big role. We're just not there in terms of kind of building these quantum computers to be able to say something quantitative about it. It's kind of still an evolving tool and not yet ready for kind of mass use in these sort of contexts.
I recently had a UF publication bragging about Hypergator as the most powerful computer associated with a university in the country.
Yeah. The Hypergator cluster here, for those of you who don't know, is really a top-of-the-line facility we're very lucky to have.
Not quite big enough, I guess.
Yeah.
Yeah. Earlier, you referred to a delta T, the difference in time when lensed images of quasars arrive at your eyeball. What values have you found for delta T?
Very good. It's really amazing. So delta T for without gravitational waves can be roughly about 100 days. And you think about like how remarkable that is. I have two images in the sky. And naively, if you were, like a scientist 100 years ago, you would just stare at these and not understand that they're the same thing. But what you would see is that you see a flash in this image, and 100 days later, you see the same flash happening here. And you can see that again and again and again, because things flash all the time. So that's kind of roughly what you're seeing. Is you're seeing two images go up and down in their brightness with a sort of relative time scale again and again and again in your telescopes. And it could be roughly a day, it could be 100 days. It's kind of a typical amount here. It's pretty long. And it's really amazing. You can see the same thing in two different images.
Back to some real simplistic stuff.
Yeah.
Has anyone ever seen a black hole? Now, I get it that light can't escape, but I've read someplace that as stuff gets sucked into it, it burns them up. Has anyone ever taken a picture of a black hole?
Yeah, it's actually an amazing achievement. So there's an experiment called the Event Horizon Telescope. It's released its first results maybe about 6-7 years ago. And what they did is they imaged very massive black holes, like the one in the center of our galaxy is one of them. One was in Andromeda. And they stared at it for a very, very long time. And they used multiple telescopes around the Earth to do this. It's a very challenging experiment. But what they were able to show is that the black hole in our center of our galaxy is kind of exactly what you'd expect. There's a sphere of light that's shining around it and a black center in a circular pattern, totally consistent with what you expected by the gravitational measurements of stars that are orbiting this thing. So it's really a remarkable achievement that they were able to make this sort of picture.
Black holes that are at the center of the universe or center of the galaxies, does each galaxy have a singular massive black hole, or are there multiple black holes that are massive?
So it depends on the galaxy. There's different kinds. However, the ones that produce these sort of gravitational wave signals that I mentioned are precisely multiple black holes. So they're in a binary. It turns out that the Milky Way, just by bad luck, I suppose, doesn't seem to have multiple black holes in the center. We seem to have just one very heavy black hole in the center, and that's it. But other galaxies have more than one black hole orbiting each other. So it depends on kind of the history of this galaxy. You could be in either situation.
A second question that I've got is, are there devices, telescopes, whatever, coming online that are going to be impacting your understanding, that are, you know, on the horizon, that are of the type that James Webb is in terms of massive impact on our knowledge?
I would say one of the biggest revolutions which is coming is not in the form of a telescope in the electromagnetic spectrum, but of the LISA experiment that I briefly mentioned. This is a sort of LIGO experiment in the sky. So that one is supposed to be starting to fly up there within a decade. It's not a very, very far future experiment. It's kind of coming up. And it's going to totally revolutionize what we can do in this sort of field. So there we're going to have a laser source over here. We're going to have 2 different satellites that are going to be floating around. And that laser will fly to these satellites. There's mirrors on the satellites. And it'll come back and it'll study it. Very similar to LIGO. And this will be able to look for much, much lower frequency gravitational waves because the satellites are far. LIGO is a few miles, roughly, 2 kilometers, so it's a mile and a bit, in size. These sort of LISA experiments, we're talking about 1 million times that. So these sort of huge baselines that we like to call them, they can look for lower frequency gravitational waves and look for a whole new type of phenomenon. So that's kind of the one that I have on my horizon, kind of excited about, kind of revolutionize, I would say, this sort of science.
I understand gravitational waves travel at the speed of light. And I wondered if there's any additional information that was useful comes out from red shifts of that those waves.
Yeah, absolutely. I mean, that's how we know how old something is. So if you have some binary that's kind of pointing in some direction, so the redshift phenomenon that I was just alluded to is the fact that frequency that we see is not the frequency that's emitted. If I'm shaking my hand at, let's say, 1 hertz over here, if you're very, very far away, you'll detect the gravitational waves that I'm producing in a little bit of a different frequency. It'll be redshifted. Meaning it'll reduce in frequency a little bit relative to the one that I'm actually shaking my hand. And that's because of universe expansion. It's a very subtle phenomenon. And we use this feature to learn about the black hole systems. If the black holes were further away, they'd have a different gravitational wave frequency than they do otherwise. So it's a very interesting and useful kind of phenomenon.
If I'm understanding correctly, when you said that there are multiple black holes inside the centers, let's call it, of galaxies, and that the detection that you're doing is detecting when some of those black holes merge, can you then pinpoint exactly which galaxy it was that this occurred in? Or are they too far away to really pinpoint it so specifically?
Very good. So that would be hopefully kind of where we're going. It's tough. The pulsar timing experiment, the angular resolution, that's what we like to call it, is not very good. So it could tell you in the future, it could tell you that a black hole merged with another black hole in this direction. But that's kind of as good as you can do. And then you can go with your visual telescope and start staring in that direction and say, is there any candidate galaxies that could hopefully match this event or not? And people are doing these sort of searches. And in 10 years from now, I suspect we'll be able to do just that. Right now, it's in the early goings. We've done these sort of like what's called targeted searches along these lines, where we say, let's catalog all the different kinds of galaxies we expect in different regions and try to match them to gravitational wave frequencies and try to pinpoint where they're coming from. But yeah, it's still early going. So the future will probably be able to do that, but right now it's still too early.
Another question? Okay. I have a question at the end.
Mm-hmm.
Actually, I have two questions.
With all the, with all the revelations in the last 15, 20 years, the universe has had to be 14 point something or other. Has there been any evidence to be able to continue to corroborate that time frame, or is that we find stuff that's older, is that we think that time frame actually goes back further than the 14.6?
Very good. So that's something that we're actively trying to measure in different ways. One way you can measure that is by studying the locations of objects around us and watch them expand. And you can infer the age of the universe that way. So you look at different supernovae or different quasars or different sources, see how fast they're moving away from us. And because they're moving away at a certain rate, we can infer how old the universe is. That's one way. We can also measure by studying this light from the early universe. If you measure the light here, you measure the light here, you study its properties. If you do a very detailed study, you can also infer the redshift that the light experiences, the change in its frequency as a function of time. And you can infer the age of the universe that way. Something amazing that's happened in the past only 5 years is that these two methods don't agree. It turns out that they're off by about 10%, 5%. So the question is, what's happening? And we don't know. Maybe one of the methods, the analysis is not working well. Maybe it's some fascinating fundamental physics that we don't understand. We'll see what the answer to that is. Though I should say gravitational waves have a hope to try to solve this discrepancy. So we can also use the redshift of gravitational waves to infer the age of the universe that way too. So the hope is that we'll have a third method to look for the age of the universe and kind of nail down what's really going on here.
Well, that kind of ties in with what was rolling around in my head. You mentioned that these supermassive black holes are on the other side of the universe, which is really saying that we're looking at something that's very ancient that happened a long time ago, like 10 billion years ago, and it's no longer there. We just see the effects of it.
Totally correct. Yeah.
So it's like, it's all so unreal.
You're seeing a flashback of the past, right? You're seeing a video of the past. That's all you'll ever get to see. It's always a video of the past. But that's what we see. We can only ever have access to what's happened a while ago.
So over time, energy, because of entropy, becomes mass. So these enormous sources of energy from the past are now some form of mass, not just black holes, but something that's no longer radiating energy. Is that dark matter?
That's an interesting question. So that's a little bit of a question which I have not addressed at all, which is kind of, there's something about the universe that's a really mystery. We have matter around us that we don't understand at all. We don't know its properties. We don't know what it's doing. We just know that it gravitates. And that's dark matter that Phyllis just mentioned. And we don't know what's making it up. It's possible that to some degree it's made up of black holes that are old and now no longer emitting light. But we know that they're not ordinary black holes because we can infer the presence of dark matter to being present already during a very, very early period of the universe evolution, well before we expect black holes to ever persist from star explosions. So it's unlikely that these sort of quasars that have died down are making up the bulk of dark matter today, but we almost know nothing about what dark matter is, and we just don't really know a ton about it.
Yeah, well, dark matter is like what zero was originally. It's a placeholder.
Yeah, it's a placeholder. Yeah.
It's a placeholder.
It might be black holes. And in fact, if it's black holes, they're a very special kind of black hole. They're what's called a primordial black hole, ones that come from the very early universe. It could be something else. We'll have to wait and see. And a lot of what I think about is trying to understand what is the nature of dark matter and how to look for it in an experiment.
Okay, and then a couple of last questions. One is that I understand that UF has a 15% interest in a radio telescope in the Canary Islands. Is that of any use to you? Your program, your group's research?
I'm not sure which telescope that's referring to, but I'm not working on one related to one in the Canary Islands.
Okay,
I'm not sure. Yeah.
okay.
The primary telescopes that I've been working with are things that sort of radio telescopes. They're often very, very big facilities. They can be, there's one in China that we don't have access to, but it's amazing. It's like almost, I think, 500 meters in size,
Oh.
a gigantic dish. We have also very impressive ones here in the US. And I'm also looking at things like the James Webb Telescope and what's called DESI, another experiment, sort of satellites that are operating.
Yeah, okay. Well, we have a question, I think, from our Zoom audience.
That was my comment.
Okay, so a question from Zoom? Bill Berg?
Yes, thanks. This has been fascinating, but my scientific work was much. Trying to compare it. You mentioned earlier that you had to have a lot of balance between. I guess I'll call it theory. That's what I would have called it, and reality, and what you really can point to as something physically happening. And I'm amazed that you can do that. I can't do that. So the question I have really is very fundamental one, and maybe it's a very simple one, and that is, you gave the analogy between auditory processes and the medium that sound travels through is air, and that's particles, real physical particles. But when you move now to space-time, I'm just totally lost. I mean, I understand what they're referring to, but it's not a. Does it have a physical presence? I mean, what is it that you can have that you can actually measure? Can you measure it?
So what I would say, what you can measure, the physical thing to talk about is always going to be some experimental observable. In the case of LIGO, what they're measuring is the arrival time of light coming in as it's going from location to location, and that gets modified in the presence of gravitational waves. So that's the observable. It's the fact that gravitational waves modify the propagation of everything around us, and it's going to be a minute deformation of these properties of arrival times, of distances. They all get modified because of gravitational waves. Now, in terms of building that intuition, it's tough. The sound waves are kind of a nice thing because it has a real medium. We understand the collisions of particles going from location to location very intuitively. For space-time oscillations themselves, they're a more abstract notion, but they're very physical in terms of what they do. They modify distances and times.
Anything else? Okay.
You're assuming that gravitational waves are what is impacting that. Is there potentially something else?
So that's kind of what I was getting at with the sort of proof. In the case of pulsar timing, there's always a fear that you're going to fake your signal. How do I know that the timing of some pulsar gets deviated with gravitational waves and not something else? Maybe my clock is bad. I have to be very, very confident my clocks are so good. And the reason why I have that confidence is because I have more than one pulsar. And I see the same signal with a certain correlation pattern across the sky. Without those correlations, I wouldn't have the confidence. And the same goes with LIGO. With LIGO, they have 2 experiments that are operating. It's not one of them, well, now it's like even more than 2. But they saw the same signal in 2 different experiments that are separated by hundreds of kilometers or miles from one another. So you have confidence because you're seeing the same thing in some unique way. In every experiment, you have to convince yourself and the whole community that you're sure you did the thing, not just hopefully you did the thing. And you require some level of the sort of how are you so sure? You need that sort of proof. And different experiments have that proof in different ways. But these sort of correlations are how we did it with pulsar timing. With LIGO is the multiple experiments that gave you the confidence in the result.
I wanted to follow up on a question that Henry asked earlier, to which you said that in the early universe, there were some really, really heavy stars that we don't see anymore. So that to me is kind of a data point. So what was different or weird in the early universe that enabled that to happen that isn't around anymore?
Yeah, fascinating. It's because the early universe was extremely uniform. So our current universe, you look around, it's extremely non-homogeneous, right? I see galaxies that are forming, and within a galaxy, the stars that are sprinkled around, the gases everywhere in this sort of chaotic looking way. And it's because the universe processed itself. Gravity acted to form these sort of different clumps of matter in different complicated ways, and that gives rise to a lot of rich phenomenon. The early universe was much more boring in that sense. It was extremely uniform. You look around everywhere, you see the same thing. And it's because galaxies have not formed yet. You didn't have that sort of gravitational clumping. And in a much more boring environment, you can build much bigger stars. There's less disruption that's happening. And it kind of enables the possibility of very, very big objects collapsing in themselves.
Wow, thank you so much. This has been fascinating, and I know that our audience, only 25 people, but obviously from the questions, a lot of questions. Yeah. So thank you all very much for coming, and thank you, Professor Dror.
My pleasure.